We are going to discuss the day 2 session of the continuous topic on mission instruction and addressing modes. So today's session we are going to discuss with few questions which is asked in our GATE exam. So here this is a question like they are asking to match. Okay, so left hand side they have given with some set of instructions. So we need to tell which type of address it belongs to. So according to that we are having the options here. Okay, so here A of 1 equal to B of j. So here what happens, it is where from this location whatever the value is there, we are just initializing to another location. So it is like what my index addressing mode. So this will be matched with this one. So next is what means while star A plus plus. So A plus plus in the sense what means it is an auto increment. Okay, so it is like auto increment. So auto increment in the sense we are using star A plus plus. So after initial it will be incrementing. So the meaning of that A plus plus means assign and then increment. That is the meaning. Okay. So this instructions will belong to this auto increment. Next, int temp equal to star x. So here this third one, the temp is assigned the value of what na int type. That only they have given here also. And that is stored at the address which is contained in this x. Okay, so it is indirectly we are moving that value. So this will belong to this indirect addressing mode. So 1B, 2C and 3A. So what is the option means? The answer will be what means our C. Okay. So the explanation part only they have given here. So here under the mission instruction, as I said previously, it is nothing but what now? It's a set of instructions. Okay, so it is what now? It's a set of instructions executed directly by a computer's central processing unit. Okay, central processing unit, that is our CPU. So each instructions perform a very specific task only, such as load, jump, or any ALU operations on certain unit of data in the CPU registers or memory. It will be performed. So every program will be directly executed by the CPU, which is made up of a set of series of instructions. So what will be the general format of the mission instructions? Means we can have the label followed by the mnemonic, followed by the operand or whatever one or more operand. And then if I want to have any comments, semicolon followed by that, I can have that comment. For example, so label I'm using here. So mnemonic code I'm using here, move. So like this, we having many mnemonic codes. So R5, hash 25H means that here the value immediately will be stored into the register R5. So that is the meaning of this instruction. Okay. So we are loading 25H into R5. Okay. So this is how we'll be writing the mission instructions. So we will see next instructions. What are the types here? So data transfer instructions, arithmetic instructions, logic instructions, string manipulation instructions, control transfer instructions, loop control instructions, processor control instructions, and some examples. So we are going to see under this mission instructions these types. So first, data transfer instructions. So here we will move or load the data into the input to which we need to get the output. So what are the instructions we'll be using here? So move. If I'm using move means it will be moving a byte or word to a register or a memory. In out means here the input byte or word from port or the output port to the port. Okay, so input byte or word from a port or else output word to the port. So vice versa for this in and out. LEA is nothing but what? Load effective address. Okay, this instruction also we can use. and then LDS, LES, so which is acting like a load pointer, which is using a data segment. Okay, there is some extra segment. And then push pop. Push in the sense we can push the word onto the stack. Pop means we can remove the word off from the stack. So this is about the instructions push and pop. And XCHG, which is nothing but we can exchange the byte or word over here. So that is the meaning of this. XLAT, which will translate the byte using our lookup table. So using these instructions, we can add the data. Okay. So for using this move, if I'm just telling move A comma B, in the sense whatever the content stored in B, that will be moved to A. If I'm using move R1 comma R2 means from R2 the content will be moved to Rn. So the meaning of that is that one. Okay. So our next one is our arithmetic instructions. So arithmetic instructions, normally we know what are the arithmetic operations we'll be doing. Add, subtraction, increment, decrement. If I want to convert the byte or word, if I want to compare, all those things we can do under this arithmetic instructions, using this arithmetic instructions. For example, add a sub. If I'm just giving means if I want to add any two values present in the register means if I'm giving add, but everything should be normally we will be using the capital letters only for the instructions. So if I'm giving add R1 comma R2 means what? Like here the both the values will be added and that will be stored in R1. So to the destination register it will be stored. So that is the meaning of this add. Sub means here it will be doing the subtraction operations. Okay. So add ADC means here our carry will be coming now. If I'm adding two values also, subtracting some values also, some carry or the borrow will be coming. Right. For addition, the carry will be coming. For borrow, in subtraction, we'll be having it. So for this, we'll be using the instruction ADC and SD. And INC is nothing but what now for increment and then decrement. So increment or decrement by or the word here we can use over here. Okay. So next is what means NEG in the sense what now negate byte or word. So that is our 2's complement. CMP in the sense what now we can compare the byte or word. So subtract without storing. So mul or div in the sense what now multiply or divide the byte or word. Okay, so that is using our mul and div. So I mul or I div is nothing but what now integer multiply divide byte or word. Okay, sign. So CBW or CWD is nothing but what? It will convert byte to word means CBW, CBW, CWD means word to double word. So like that. So next is what now? AAA, AAS, AAM, AAD in the sense what now? Here the ASCII adjust for addition, subtraction, multiplication and then division. DAS in the sense what now? It's a decimal adjust for addition and then what now? Decimal adjust for subtraction. So these are the instructions we are using over here. Okay. The next is our logic instructions. So logic instructions means what are the logic instructions we'll be using here means and or exclusive or that is our XR or shift or rotate or test, all those things we can do using our logic instructions. Okay, so here not in the sense what not logical not of the byte or word like one's complement we can take using this not. Not A means if it is having a 1 means that 1 will be converted to 0. 0 means 0 will be converted to 1. So like vice versa. Where the byte of word that thing will be what na? Reverse. So that only we are telling as a ones complement over here. For this instruction, not. And normally we know logical and of byte over. So we know the truth table. According to that, it will be doing that calculation. Okay. So in the truth table, 0, 0, if I'm having means if I'm doing the AND operation means it will be also what output will be 0. 1, 1 means 1. If anything is 0 also output will be 0. So 0, 1 for this also it will be 0. So 1 represent what na true and 0 represent what na false. So according to this the values will be what na calculated. So this is about what na AND. So or in the sense any one byte whether it's 0 or 1 so it will be taking that. So that is about for what na R. XOR in the sense what na it's a logical exclusive R of byte or word. Okay. So next is what na text byte. Okay, so we can test a byte or word where and without storing that values, all those things we can do using this test. And SHL, SHR in the sense what the shift left, shift right. So logical shift rotate instruction that is what means a shift left and byte or word so that we can do. Okay. So SAL, SAR, which is nothing but arithmetic shift left and right byte or word where we are having the carry left over. And this instruction ROR, which is used for rotate left, right byte or word by one, all those things for using this instruction. And RCR means it is rotate left, right to carry byte or word by one or zero. Okay, so this is about what na logical instructions. So next, if I want to do the manipulation using the string, if I want to compare or if I want to store or if I want to load some data, all those things I can do using this string manipulation instructions. So load means I can load the value, store the value, or if I want to move from one location to another location, I can do using this move. Or else if I want to compare any two things, I can do using this compare. Or else if I want to scan any bytes, so using the scan, all those things we can do for the byte or the word. So using what instructions we can do means move yes where we will be moving the byte or word string. Move SB or move SW means what? Here it will be moving the byte or it will be moving the word string. Okay, so that will be coming under what now? Move SB, comma, move SW. Next is CMS. Here it will be doing the comparison of the byte or the word string using this CMPS. Next is SCAS. Yes means can byte or word string. We are comparing to A or AH. LODS or STOS means here we are loading or storing a byte or word string to AL. So next is our control transfer instructions. So control transfer instructions in the sense what means here we'll be having this JMP. Okay, that is what unconditional jump. JNC, that is what jump. Okay. So JMP in the sense what now it includes a loop transfer and subroutine and interrupt instructions. JNZ means the jump till the counter value decreases to 0, it runs the loop till the value stored in CX becomes 0. Okay, so this is about what now control transfer instruction. So next is what now loop control instructions. So loop control instruction in the sense what now loop, where loop unconditional count in CX or short jump to target address or loop E set. Okay, loop if Z equal means 0, count in CX and short jump to target address, so that will be coming under loop. Loop NE or loop NEZ means if the loop is not equal, that is not 0, count in CX, short jump to target address. Okay. Next is JCXZ, jump if CX equals 0, used to skip code in loop. And the subroutine and interrupt instructions like call or return. Okay, call in the sense if I want to call the procedure inside or outside the current segment, I can do using this call. RET means if I want to return from the procedure, I can return using this RET. So into in the sense what not the software interrupt or interrupt with overflow returns from the interrupt, all those things will happen that will be using under this loop control instructions. So next is what now your processor control instructions. So processor control instructions like what now on the flag manipulation, say STC, CLC, CMC. So STC for set, CLC for clear, and CMC for complement carry flag. So all those things will be coming under this STC, CLC, and CMC. And then STD, CLD for set or clear the direction flag. STA in CLI for set or clear interrupt enable flag. So all those things will be coming under this one. Next, push F, pop F. So push F in the sense push flags onto the stack. Pop flags off the stack. So these two things will be coming under this processor control instructions. So we will see one example. In the following code segments, A, B, C, D are the variables. The 5 variables A through E correspond to the 5 registers. So here I am telling us 5 registers like what now on the $S0, $S1, $S2, $S3, $S4 respectively. A stands for $S0, P stands for $S1, and C stands for $S2, and D stands for $S3, and E for $S4 respectively. And here what is compiled MIPS code for C code? So MIPS multiple instructions per second for C language. So we are asking here. So here we having the coding like if A equal to B. Okay, A and B are equal means we are going to do the calculation addition of B and E and we are going to store in C. Else means I am going to subtract D and E and then I am going to store in C. Okay, so here if this is the case, if A equal to B, then this, else this means according to this instruction I am going to write the mission instructions. So how I can write? So BNE is nothing but branch not equal. So when this is equal only, it will be doing this one. Else it will be doing this one. So here BNE means branch not equal. So $S0, $S1, that is S0 which represents the variable A and S1 which represents the variable B. Okay. So when this two thing is not equal, so B and E in the sense what now? This S0 and S1 is not equal means it is going to add what means D and E. D and E in the sense S2 and S3. Sorry, S3 and S4, right? And then this added S3 and S4 I am going to store in another register S2. Okay, so that one. So if it is equal means it will be doing this one. If it is not equal means it will be going to this else part. So here I am telling branch not equal. So branch not equal means I am going to perform this subtraction thing. But this is a false case means it will be coming to this part. So when this is true in the sense, okay, so branch not equal means it will be coming to this part. So here S0, S1 when it is not equal, it is going to do the subtraction. So D and E, which means S3 and then S4. So S3 comma S4, I'm going to subtract and then I'm going to store the value in S2. So S2 register which represents our C. And if it is false means it is going to execute add D and E. D and E in the sense S3 and S4 register it is going to add and it is going to store in S2. So add S3 comma S4 and then it is going to add and going to store in S2. So after doing this instruction, exit means it will be coming out. Okay, so this is about our this particular instructions, how we are writing using this mission instructions. We saw one example. So these are the mission instructions, we any add, sub, all those the mission instructions what we saw previously. Okay, so mostly arithmetic answer instruction like move, add, sub, like that and all we'll be using mostly. If I want to jump from one instructions to another instructions, I'll be using this JMP. Okay, so loop control instructions means I'll be going for this call and RT and all I'll be using mostly. Okay, and the loop control instructions and under processor control instructions, our pop flags, CLC clear, all those flag manipulation operations we'll be doing here. Okay, so apart from this, here we having the pipelining concept. Actually, what it means multiple instructions are overlapped in executions. So the computer pipeline is divided into stages. Like each stages will be completing a part of the instruction in parallel. So the stages of one will be connected to the another to form that pipe instructions to enter at one end and the progresses through the stages and it will be exiting at the other end. Okay. For example, if I'm taking a non-pipeline approach for laundry, I'll be placing the set of dirty clothes in the washer. When the washer is finished, means I'll be placing the wet load into the dryer. And after the dryer is finished, means I'll be placing the dry load on the table and I'll be folding. When folding is finished, means I'll be giving all those clothes to the respective roommates. Okay. When your roommate is done, means start over with the next dirty clothes. Okay. So we are going sequentially one by one after another. But what happens now, the time gets waste over here. So see here with the diagram I have mentioned here. So here we are taking up with the four tasks. One, we are placing the dirty clothes on the washer and then the washer is finished means again the wet load into the dryer. When the dryer is finished means again we are placing the dry load onto the table and we are folding that. When the folding is finished means we are asking the roommate to put the clothes away. So these are the four steps. So actually we are doing one by one. Okay, this time after finishing only, it will be taking the next dry, dirty load. So like that, it will be moving. But here the analogy for pipelining is after putting the dirty clothes to the washer, when the washer is finished, we are putting in the wet load. Okay, so we are facing during that time.
மணியாகி போச்சு பிடிச்சி மேலே வச்சிருக்கேன் எடுத்துன்னு போயிட்டு அதில் மாமா வந்தோடனே எவ்வளோ இருக்குன்னு எண்ணி பார்த்துருவோம் இருக்கும் இருக்கும் ஆனால் முழுசாக இல்லை நான் கம்மியாக இருக்க மாட்டாது 1500 கம்மியாக இருந்தால் இருக்கும் வச்சிருக்கேன் எல்லாம் இருந்தால் இருக்கு எவ்வளோ 1,00,000 ரூபாய்க்கு இருக்கும்
இப்போ நான் நகை எடுக்கல நகை எடுத்துட்டு போகணுன்றீங்களா நகை எடுத்துட்டு போகணுன்றீங்களா என்னென்ன வாங்கணும் டக்குன்னு சொல்லுங்க எனக்கு
எடுத்துட்டு போனானே வாங்க முடியும் வேற என்ன வாங்க முடியாது வீட்டுல என்ன பண்ணுது அவர் வாயில் வந்து கொடுத்தா கையில போட்டுக்குவாரு
காப்பு மட்டும் வாங்கணுமா
ஆமா வேற என்ன
வேற என்ன வாங்கணும்
வேற ஒண்ணும் வாங்க தேவையில்ல
காப்பு எத்தனை பவுன் வாங்கணும்
2 பவுன்ல வாங்கினாதான் முடியும் அதை விட கம்மியா வாங்கினாதான் போட முடியும்
சரி ஓகே ஓகே
எடுத்துன்னு போயிட்டு அவருக்கு 2 பவுன்ல அவருக்கு பார்த்து வாங்கிருந்தா காசு அதுல இருக்கு அதை எடுத்துன்னு போயிட்டு எவ்வளவோ அதை நீ வாங்கிக்கோ.
So like this we'll be doing this one. Okay, so this is about what a laundry analogy for pipeline. Okay, so here the technique used in advanced microprocessor where the microprocessor begin executing the second instruction before the first has been completed. So the pipelining is nothing but a series of stages where some work is done at each stage. The work is not finished until it has passed through all the stages. So with pipelining, the computer architecture allows the next instruction to be fetched while the processor is performing arithmetic operations. So holding them in a buffer close to the processor until each instruction operations can perform. Okay, so it is not waiting for the next one. While this place is finished means again we can make the another set of dirty clothes we can put in the washer. So we are not making anything to be in a rest place. So without waiting for this, see here from 6 p.m. to morning 2 a.m. I'm doing the process for 4 set of dirty clothes. Okay, 4 times I'm just putting. For this much time it is taking. The same thing I'm just doing by taking only 4 hours and just finishing all those 4 set within this 4 hours. So this is the thing about this laundry analogy for pipeline. Okay. So here what is the instruction, multiple instructions per second MIPS. So this set of instructions will be classified into 5 steps. So what are the 5 steps in the sense? We'll be fetching the instructions from memory and then we are reading the register while decoding the instruction. The regular format of MIPS instructions allows reading and decoding to occur simultaneously. And then execute the operations of calculate and address. And then access an operand in data memory. And then we are writing the result into a register. Okay, so all these are the 5 steps over here. So first fetch instructions from memory and then read the registers while decoding the instructions. And the regular format of MIPS instructions allows reading and decoding to occur simultaneously. And then we are execute the operations or calculate an address. And then we are access an operand in data memory. And we are writing the result into the register. So these are the steps we are doing over here. Okay, so next is what? Instruction pipeline. Okay, so instruction pipelining. So instruction cycle is also known as the fetch, decode, execute cycle, or simply we can say as a fetch, execute cycle. So here it will be following from boot up until the computer has shut down in order to process instructions. So it is composed of 3 main stages. So what are the stages? Means first the fetch stage, and then the decode stage, and the execute stage. So this is a simple diagram illustrating the individual stages of the fetch, decode, execute cycle. In simpler CPUs, the instruction cycle is executed sequentially. Each instruction is being processed before the next one is started. So in most modern CPUs, the instruction cycles are instead executed concurrently and often in parallel through one instruction cycle. Okay, so this is about what instructions are executed in a parallel manner. Like. So next is the clock cycle. So a computer processor or CPU speed is determined by the clock cycle. What is meant by this clock cycle? Clock cycle, which is nothing but is the amount of time between two pulses of an oscillator. Generally, the higher number of pulses per second, the faster the computer process can do process information. The clock speed is measured in hertz, often either megahertz, that is MHz, or gigahertz, that is GHz. For example, a 4 gigahertz processor performs this set of clock cycles per second means a computer processors can execute one or more instructions per clock cycle. So depending on the type of processor. So early computer processor and slower CPUs can only execute one instructions per clock cycle. But modern processor can execute multiple instructions per clock cycle. So the basic measure of performance, so the CPU time equal to clock cycle by program into seconds by clock cycles. So cycles count into clock cycle time. So this is about the CPU time. Normally the clock rate is equal to 1 by clock cycle time, which is inversely proportional. This clock rate. Okay, so clock rate is nothing but I will be writing like 1 by clock cycle time. So performance is nothing but what? It's the inverse of our CPU time. So a clock in a digital system creates a sequence of hardware signals where hardware events must occur at these predefined clock ticks. So the clock cycle time or just a clock cycle or even a clock period is a time between two clock ticks. So the clock cycle time is measured in nanoseconds, that is 10 power minus 9 seconds, or microseconds, that is 10 power minus 6 seconds. Okay, so this is about what? A basic performance measure of performance. So SI multiples of hertz, that is our HZ. So submultiples, so what are the value for this? What is the SI symbol and what is the name? Okay, so see here, value SI symbol name here, 10 power minus 1 hertz. Okay, 10 power minus 1 hertz. So SI symbol is DHZ. So the name is Desi Hertz. 10 power minus 2 hertz. The SI symbol here is CHZ. The name is centihertz. Okay. So next is 10 power minus 3 hertz. That is MHZ. That is the SI symbol. So the name is what? Millihertz. 10 power minus 6 hertz. That is mu HZ. That is what? Microhertz. 10 power minus 9 hertz. That is NHZ. That is a nanohertz. Okay. So like that, for submultiples and multiples, we having the set of values and the set of SI symbols and the name over here. Okay. So here the example, machine A runs a program in 100 seconds. Machine B runs the same program in 125 seconds. So machine A runs a program in 100 seconds. Machine B runs the same program in 125 seconds. So the performance of A divided by performance of B, as I said previously, performance of A in the sense what? The execution time of B. That is 1 by performance of A means 1 by CPU time of A. Performance of B in the sense what? It's 1 by execution time of B. Right. So if it is going up and down, it will be what? Execution time of B divided by execution time of E. Okay, so it will be what means 125 by 100, so it will be 1.25. So that means machine A is 1.25 times faster than machine B. So that means machine A is 1.25 times faster than machine B. Okay. So pipeline hazards. There are situations in pipelining when a next instruction cannot execute in a following clock cycle. So these events are called what now? Hazards. So there are three different types of hazards are there. One is structural hazards, data hazards, and control hazards. Okay, so the situation in pipelining where the next instruction cannot execute. So that event only we are telling as a hazard. So data hazards in the sense what na, the instruction or data hazards is a situation in which the pipeline is stalled because the data to be operated on or delayed for some reason. That is what the data dependency. Okay. So mul R2, R3, R4 in the sense what na, I am doing the multiplication of all the three. R2 into R3 into R4 and finally the multiplied value that will be stored in R4. And again add R5, R4, R6 in the sense what na, again it will be adding everything and that will be stored in what na, R6. So the number of clock cycles for pipeline stall is 1. Number of clock cycles for pipeline stall it will be what na, 1. Okay, so here the cycles 1 to 8 we have represented, and for first instruction for multiplication, fetch, decode, execute, write. For multiplication, during the addition, I want the value from this multiplication. What value I want? I want the value of this R1. So till this get manipulated, this execute till it get right to this R4, I need to wait in the next part. So this dotted lines which is waiting, and then only the decoding execute write operations will be performed. So the total cycle will be what na, 8 clock cycle. So this is waiting for data. So that only we are telling as data hazards. And the structural hazard is a situation when two instructions require the use of a given hardware resource at the same time. Okay, so the instructions like load x of R1, R2. When I'm just loading the data. Okay, so where two instructions require the use of the given software. Okay, or the given resource at the same time, it's waiting. In the sense, we are telling that as what na, structural hazards. Next is what are your instructions or control hazard. The purpose of instruction fetch unit is to supply the execution unit with a steady stream of instructions. So whenever the stream is interrupted, the pipeline will be starting, which is termed as an instruction or control hazards. So example, our branching instructions, we saw no B and E. So that and all will be coming under this hazards. For example, we will consider one situation. So this is a sequence of mission instructions which is given below. So in our sequence R0 to R8 general purpose registers. So in the instruction shown, the first register shows the result of the operation performed on the second and the third registers. This sequence of instruction is to be executed in a pipelined instruction processor with the following 4 stages. So what are the 4 stages in the sense? First stage, instruction fetch and decode. Okay, so these are 4 stages I need to do it. So here, these are the 4 stages. Okay, so these are the 4 stages I need to do it. So instruction fetch and decode, then operand fetch, and then perform operations, and fourth one, write back the result. So instruction fetch, operand fetch, and write back stages takes one clock cycle each for any instructions. And PO stage will take what now? One clock cycle for add or sub instruction. And 3 clock cycles for multiplication instructions. And 5 clock cycles for division instructions. Okay, so this is the set they have given. The pipeline processor uses operand forwarding from the PO, that is perform operation stage, to the OF, operand fetch stage. What is the number of clock cycles taken for the execution of the above sequence of instructions? Okay, so here the 4 stages. First, instruction fetch and decode IF, operand fetch means OF, and perform operation means PO, write back the result means WD. Okay, so here the number of clock cycles taken for the execution of the above sequence of instructions. So how much I need to calculate? So see here. So already they have told this 4 stages where there is instruction fetch, operand fetch, and then this write back will be taking only 1 clock cycle. And this processor perform operation stage takes 1 clock cycle for addition, subtraction, and multiplication to 3, division to 5. Okay, so here what is the instructions they have given? First mul R5 comma R0 comma R1. So we are doing for multiplication, how many clock cycles? 3 clock cycles. Okay, so for instruction fetch and for operand fetch, it is taking only 1 clock cycle. As it is multiplication, it will be taking what? 3 perform operation cycles. So PO, 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 and then write back, that is last one. So again, what happens? I am going to do this div R6, R2, R3. So for division, how many clock cycle? 5. So I want this value. So again, in the second clock cycle, instruction fetch, and then operand fetch, and then it is waiting for this result to be written, and then 5 clock cycle for perform operation, and then write back. And then what means here? Third, addition and all, they having only 1 clock cycles. So again, instruction fetch, again here operand fetch, again we are waiting till the write back, again only 1 clock cycle for addition, so perform operation, and then again write back. And then again for subtraction, the 4th one, instruction fetch, again I'm just doing this operand fetch, and then it is actually subtraction now, so I need to wait till write back of previous instructions. So perform operands operation, that is 1 clock cycle, and then write back. So totally 13 clock cycle I need that. So I will be going with the option 13. So next, what is meant by this RISC and CISC? RISC is nothing but it's a reduced instruction set computing. CISC is nothing but complex instruction set computing. Okay, so CPU time equal to seconds by program, that is instructions by program into cycles by instruction into seconds by cycle. So what is the difference between CISC and RISC? It's a complex instruction set computer, reduced instruction set computer. It is emphasis on the hardware with the emphasis on software. Here the multiple instruction size and forms. Here instruction of same CPU format. Here the less registers are used. Here we are using more registers. And here more addressing modes we are using. Here fewer addressing mode. Here extensive use of microprogramming. Here complexity in compiler. And then instructions takes a varying amount of cycle time. Here the instruction takes 1 cycle time. Here pipelining is difficult, and here pipelining is easy. Okay. So here, okay, here is one question. Consider the following processor design characteristics. Register to register arithmetic operation only, fixed length instruction format, hardwired control unit. Which of the characteristics above are used in the design of RISC processor? Okay, so we are going with the option D, because For RISC processor, reduced instruction set computer, I need to have the register to register arithmetic operation, fixed length instruction, hardware control unit, all the three things should be there. So what is the difference between this call and jump instruction? So call instruction is used to call a subroutine. Okay, so subroutines are often used to perform the task that we need to be performed frequently. So JMP instruction is used to cause a PLC, that is our programmable logic control, to skip over many instructions. So the difference here, SIC is nothing but simplified instruction computer. SIC, it's extra equipment that will be added. So it's a hypothetical computer that has the hardware features which are often found in this real missions. So here also SIC mission architecture, where we'll be having the memory and the register. Same thing that here accumulator means A, X means index is used for addressing, L means linkage register. So it stores the return address of instruction in case of subroutine. P means program counter, which holds the address of the next instructions to be executed. SW means status word, that is 99, contains a variety of instructions. So here memory, how it will be calculating means it's a, first of all, what is memory? It's a byte address, that is words are addressed by location of a lowest numbered byte. So 2 power 15 bytes in computer memory in the sense 1 byte equal to 8 bits. So 3 consecutive bytes in the sense which is equal to 1 per. So 24 bits equal to 1. Okay. So the status word registers. So these are the representations. So how it is represented for each one they are giving. And then hardware architecture means our parallel company, the process of how the multiple tasks are simultaneously executing on multiple processes, that one we are telling as the parallel processing. So here under Finn's classification, we are in single instruction, single data, single instructions, multiple data, multiple instructions, single data, multiple instruction, multiple data. So all those things will be coming under this Finn's classification. Why we are going means hardware architecture parallel computing is distributed along these following categories. And these are the generations of computer. And the Amdahl's law, which means the overall speed of equal to that is the old execution time by new execution time. Okay, so that is 1 by 1 minus fraction enhanced plus fraction enhanced by speed up enhanced. So this is the formula for Amdahl's law. Okay, so in next class we will see the next topic. So till this, please revise. Okay, which will be very useful for you students. Having any doubts?